Hi everyone, welcome back to Algorithm Simplified. Today we're going over minimum deletions to make array beautiful. First, let's read over the problem. So we're given a zero-indexed integer array nums. The array nums is beautiful if first it has to be even length, and furthermore, for every single even index num, its odd index num that follows right after has to be not equal to it. So we note that an empty array is considered beautiful and that we can delete any number of elements from nums. And when we delete an element, all the elements to the right of the deleted element will be shifted 1 unit to the left to fill the gap created, and all the elements to the left of the deleted element will remain unchanged. So we want to return the minimum number of elements to delete from nums to make it beautiful. So as an example, for 1, 1, 2, 3, 5, we can either delete the first, making effectively 1, 2 being a pair, and 3, 5 being a pair that we look at. It's a length of 4, and 1 and 2 are not equal, and 3 and 5 are not equal. Or we can delete nums 1, effectively doing the same thing. For example 2 here, we can either delete 0 and 5, or we can delete 1 and 4 to get 1, 2, and 2, 3 pairs. But either way, the minimum number we need to delete to make this array beautiful is 2. So let's think about what we need to do to solve this problem. Well, ultimately, this problem is a pairing problem, right? So let's think in pairs. So if we are able to pair off all of our numbers in nums, then we successfully have an even number, satisfying the first requirement. And also, we need to make sure that for every single pair that we have of some num I and num j, this I right here is not equal to nums j. We don't have any other requirements stating that the other pairs need to be not equal to the other pairs. So all we need to worry about is just the difference, or if the two elements within a pair are equal. So let's think about the first example, 1, 1, 2, 3, 5. So if we were to say start off somewhere, let's say we start off at nums 0, and we look for the first element to finish off of our pair. So in this case, since index 1 is equal to 0, that can't be the matching pair, right? That wouldn't work. So we have to delete 1 and move on to 2, index 2. And here, since 1 and 2 are the first, so 2 is the smallest index in which it is not equal to 1, this is our first pair. And then we moving forward, 3 being our opening pair, 5 is the first element, such that it's not equal to 3, so that's our second pair. So in total, we've deleted 1 element from nums array. But the problem is here we just hypothetically started off our first pairing on index 0. Well, what if the index pairing don't start until some index j, right? What if it needs to be the case that in some optimal solution, or all the optimal solutions, num 0 just isn't an opening pair? Well, actually, I'm going to claim and I'm going to prove that for any nums array, there always exists an optimal solution with num 0 being the first element of the first pair. Now that's assuming we have elements in our array. I'm going to prove that this claim about having always an optimal solution with num0 as the first element in any nums int array we're given is true through proof by contradiction. So let's set big capital S with an underline to be the set of optimal solutions, all optimal solutions for some int array nums. And let's assume for the sake of contradiction that num0 is just not part of any solution S in the big set of all solutions S. So let's denote I and j to be the indices of the first pair of some solution S, any solution S. So what this means is there will be three cases, right? So we have some solution S here, and then, we have some array that solution S has that holds even numbers with pairs that satisfy S. And the first pair is going to be nums I, nums j. And there could be more or none afterwards. So the first case is that num0 is equal to nums I. Well, if num0 is equal to nums I, then all I have to do is let me denote another solution array S prime to be the exact same thing as solution S, except I just swap S's first pair from nums I, nums j to num0, nums j. And S prime is still a valid solution, so it belongs to the big set of S because num0 is equal to nums I, and we know that 0 comes before j, making it a valid pair. So therefore, that's a contradiction because num0 wasn't supposed to be any part of any single solution in our big set S, yet we just proved that we can derive a valid optimal solution S with num0 as its first element. The same logic follows for case 2. So except this time, I denote S prime to be the same as solution S, and I swap the first pair to num0, nums I. And this makes sense because num0 equal to nums j. And since nums I and nums j were in a pair, that means they were not equal. And that means, therefore, num0 and nums I are not equal. And since 0 comes before I, this is also a valid pair in our solution. And S prime is therefore also an optimal solution in S, also a contradiction. Case 3 is the case otherwise, right? So the case where case 1 and 2 is not true. So therefore, num0 does not equal to nums I, and it also does not equal nums j. So in this case, I just set S prime to be the solution, the same thing as S, except I just swap its first pair to num0, nums I, and I just delete nums j and keep everything else the same. Right? And this works, again, with logic very similar to here, because since nums I and j are not equal to each other since they're forming a pair, and num0 does not equal nums I, we can have a valid pair right here. Deleting nums j and keeping everything else the same, since S prime itself is already a valid solution, then keeping everything else the same afterwards should still make S prime a valid solution. So therefore, S prime is a valid solution, and that's also a contradiction. So since for all three possible cases, for some generic arbitrary values of nums0, nums I, and nums j, we've proven the claim by contradiction. Therefore, we know for sure that our claim is true, that there does indeed exist an optimal solution with nums0 as the first element for any nums array we're given. And what this means in terms of our implementation is that we can indeed start our first pair or counting our first pair at index 0 for any array we are given and reach a optimal solution. So here I have an algorithm that I wrote, and it works. I've checked online. I suggest that before you look at mine, try to see if you can come up coding the solution on your own. Okay, so looking at the solution right here, what I do is first I initialize the pair index 1, referring to the index of some pair, the first element here. So this right here, this index is pair index 1 for any pair that exists. Num pairs just keeps track of how many pairs there are, and n, of course, being the length of the numbers. What I do is I just iterate through the array nums, and if the pair index 1 is equal to -1, so I set -1 to denote that we either just closed off a pair, so we don't have a pair opened yet, or we are just starting iterating through this entire array and we haven't found the first element yet. In either way, when pair index 1 equals -1, it just means that we need an opening pair element. So what I do is I just set our pair index value to I, meaning at our current index I, that is where our pair opening will be. So we'll have a new pair. There could have been many pairs before and many pairs after, or none at all. And here we just set this. This is going to be our I. Okay. The other case that we need to pay attention to is, well, if we found a pair, so if pair index is not -1, so we do indeed have a pair opened, and we found our I that closes off our pair, meaning that the nums pair index 1 is not equal to nums I. This is our second requirement, that the pairs have elements that are not equal to each other. If we found the closing pair, then all we need to do is, well, let's reset pair index 1 back to -1, meaning we've closed off a pair. Now we're looking for a new pair to open. And also that num pairs, the number of pairs we have now, we can plus equal 1. So in total, what we need to return is the minimum number of elements deleted. And we can simply do that by taking n, our total number of elements, subtracting by how many pairs we have times 2, because that's how many elements we have in our optimal solution. So then the difference between the two is how many we need to delete. In terms of big O, time-wise, so time-wise, this is O of n time, because we have one for loop and everything else is a constant operation. And then we also have O of 1 memory, because we don't initialize any sort of cache or any variables beyond a constant memory variable.